All right, welcome everyone. So in this video, we are going to jump up to another dimension. So we've talked about how we can calculate determinants of 2 by 2 matrices. We talked about how we can find determinants of 3 by 3 matrices, which relied on our ability to calculate the determinant of a 2 by 2 matrix. And now let's extend this definition to 4 by 4 matrices. So let's consider this 4 by 4 matrix A. We've got the first column of 1, 4, 2, 0. The second column is 2, 10, 5, 7. Column 3 is 3, 2, minus 1, minus 5. And column 4 is minus 2, minus 3, minus 6, and 1. So let's define this determinant just like we did with the 3 by 3 case using sub-matrices. So we can come across the very first row, and I'm going to say I'm going to take the A11 entry times the determinant of submatrix A11. So in this case, submatrix A11 would be this 3 by 3 matrix that I just circled in red. And then we do the same. We go next to A12, and because the sum of 1 and 2 is 3 is odd, we put a negative sign here, and then we multiply that by the determinant of submatrix A12. Then we add A13 because the 1 and the 3 add up to an even number times the determinant of submatrix A13. And then finally, we subtract because the 1 plus the 4 gives us a 5, which is odd. So we're going to subtract A14 times the determinant of submatrix A14. And so now what we have is A11, that was the 1 that we have over here, times the determinant of this submatrix A11, which is a 3 by 3 matrix. Then we're going to subtract, A12, which is 2, times the determinant of submatrix A12, plus A13 times the determinant of submatrix A13, minus A14, which is minus 2, times the determinant over here, I have submatrix A14. And now for each of these submatrices, they're all 3 by 3. So I would need to go ahead and for this first submatrix A11 to calculate its determinant, we would need to calculate the determinant of 3 2 by 2 matrices. And then this is what I would plug in place over here. And then we would still need to go ahead and do that same calculation for each of these sub-matrices. So for this one over here, we're going to have 3 more 2 by 2 matrices. And for this one, 3 more 2 by 2 sub-matrices that we're going to need to take the determinant and so on over here. So the arithmetic can get extremely burdensome. And that's why we'll see how we can do this with technology using Python shortly. But it's important to see this recursive relationship in that we start with defining the determinant of a 2 by 2 matrix. Then we're able to define the determinant of 3 by 3 matrices using what we know about 2 by 2 matrices. And then we define the determinant of 4 by 4 matrices based on what we know about determinants of 3 by 3 matrices. So I am not going to wrap up this calculation because it is long and tedious. We'll use Python to come up with this calculation, but I do want to take a look at one 4 by 4 matrix example on the next slide, just to get a feel for how this calculation might work. All right, so now that we know how determinants of 4 by 4 matrices work, let's consider the following example where we have this 4 by 4 matrix A. And notice that this matrix A is again upper triangular, just as we saw with a 3 by 3 case, because all of the entries below this diagonal are 0. And what we saw for the 3 by 3 case was when we had this very special looking matrix, upper triangular matrix, that the determinant wound up just being the product of the diagonal entries. So let's see what happens for this example. And just like in the case of 3 by 3 matrices, I can pick which row I want to do this expansion. And because this very last row has 3 zeros in it, that should be the easiest row to do this expansion. So I'm going to calculate the determinant of this matrix A by going along row 4. And I'm going to have a 0, plus a 0, plus a 0. So I don't even care about the first 3 sub-matrices. But now I've got my entry, which is A4, 4. And 4 plus 4 is 8. That's even. So we're going to add A4, 4 times the determinant of sub-matrix A4, 4. So in this case, A4, 4 is equal to 4. And now we multiply by the determinant of submatrix A4, 4. And that submatrix we get by canceling out all of the entries in row 4 and column 4. And what's left over now is a 1, a 3, and a -1 for the top row, a 0, a 2, and a 3 for the second row, and a 0, and a 0, and a -1 for the third row. And so this submatrix A4, 4, we can notice it's upper triangular. And what we saw is that for upper triangular matrices, their determinants can be written as the product of the diagonal entries. So in this case, it's going to be a 1 times the second diagonal entry is 2 times a -1. And this gives us altogether a determinant of -8 in this case. And we can check that this -8 would come from taking the product of the diagonal entries, which would be 4, a -1, a 2, and a 1. That gives us -8. And so I just want to close this example by stating a general fact, which is that if A is a triangular matrix, that might mean upper triangular like we've seen. That also will apply to what we call lower triangular matrices, which would be the reverse, when all of the entries above the diagonal are 0. So if we have either an upper triangular or a lower triangular matrix, then the determinant of that matrix we can calculate by taking the product of all of the entries along the main diagonal of that matrix, as we saw over here. So we saw this was true for the 3x3 case. It follows for the 4x4 case. And you can prove this in general using an inductive type of proof.